Yep. And yeah, welcome. So let's hope that you learn some useful things from this workshop, and let's hope that you have a lot of fun along the way. And as you probably would have guessed, we'll be having this workshop in Python. We'll be using the Jupyter Notebook for um, carrying out all the image processing exercises. And yep, I hope that you guys have done the prerequisite that I mentioned in the poster, and also in the email that had been sent from the IIT KGP PR email. So yep, I hope you guys have done the prerequisite. Also, uh, if my voice is not audible or if I'm breaking up at any point, please let me know, because it would be very hard for me to know. And since I'm assuming most of you will remain muted throughout the workshop, so please let me know if I disconnect in between. And also, please don't hesitate to ask any doubts or anything basically which you want to ask related to the workshop. Please don't hesitate to ask any doubts. Yep. Also, it would be great if you guys could switch off your cameras for the sake of bandwidth, and also mute yourself if you're not saying anything, so that would help cut the noise. Sorry. So assuming that you guys have completed the prerequisites, I would be continuing from that point. Rahul, could you switch off your camera? Rahul Bhattacharya. Okay. Great. So, yep, let's get started. I think there is. I'll keep this window on this monitor. Yes, the meetings will be recorded. In fact, you can begin the recording right now. There. So I have started the recording, and I will be sharing my screen now. Yeah, my screen should be visible now. Is it visible?
Yes.
Okay. So I have my system set up for this Jupyter notebook, and this Jupyter notebook is in a folder wherein I have these images: animals, Eiffel, Lena, Spot, and veggies. So we'll be using some of these images in our image processing exercises today. So having these images in the folder where the IPython notebook is present helps us import them easily. So I just let you know the configuration of basically I let you know the folder structure. Right. So assuming you guys have done the prerequisites, let's start now. So first of all, let's start with the sec. Yep. First of all, let's start with in the installation of Opencv. How would you install Opencv if you don't have it installed already in Python? So to install Opencv, all you have to do is run this command: pip install Opencv contrib Python. There.
I'm going to verify the height of this actuator is at 30 millimeters or smaller.
Could you please mute your... Yep, thank you. Yeah, so this is basically how you should install Opencv. We are installing the contrib module as well, so that all the modules of Opencv get installed. So you can, like, if at some later point you want to use some extra features of Opencv, then you have them available at your disposal. So yeah, this is basically how you install Opencv. Now let's start with some basic NumPy. So, right, I think we all know what lists are in Python. I assume you guys are a little bit familiar with Python, so you will know what lists are. So if I define a list, something like this, and if I print that list, so that list contains 1, 5, and 2. The A list variable is a list which contains 1, 5, and 2. Okay. So moving on from lists, let's move on to NumPy arrays. How do we create a NumPy array from a list? We basically take, let's say we want to create a NumPy array called ANP. We can just write this, and this will take the contents of a list and convert them into a NumPy array. So if I print ANP now, okay, I made a spelling mistake. Yep. So you can see that it converted the contents of a list into a NumPy array. So this is a NumPy array with 1, 5, and 2 now. Great. So this is basically how you convert a list to a NumPy array. But what exactly is a NumPy array? If you guys are not familiar with the concept of NumPy array, I can really quickly explain it. So you can think of NumPy arrays as a grid kind of structure. So let's say we are talking about a one-dimensional array, one-dimensional NumPy array. So a one-dimensional array has this kind of a structure. It is basically a row of data. So each cell of this one-dimensional grid is filled with either an integer or a float. Let me write that clearly. Either an integer or a float or something of that sort. It's filled with some kind of a data. So this is a one-dimensional NumPy array. What would a two-dimensional NumPy array look like? It would look something like this. It would be a 2D grid of data, and each cell would contain either an int or a float or some kind of a data. So that is what a 2D array would look like. So let's really quickly write some examples of 1D array and 2D array. Yep, 1D array. Let's call it array 1D equals, so I want to define an NP array. Okay, some people are waiting in the lobby, it seems. How do I let them in? Give me 1 sec. Yes, let's continue. So yeah, I was writing an example of a one-dimensional NumPy array. So this is basically what we wrote over here, but instead of using a variable, I just wrote the list straight out. And now if I print array 1D, yeah, we get a one-dimensional NumPy array. Great, so we know what one-dimensional NumPy arrays are. So how do we make two-dimensional NumPy arrays? So that's pretty simple as well. Let's make an array 2D. So by the way, if you guys have the environment set up, you guys have Jupyter Notebook and Opencv installed, then you guys can follow along. But if you don't have it installed, then there's no need to worry. You can just pay attention, and if you want, you can take notes. These Jupyter notebooks will be provided to you at the end of the session. So you just need to just pay attention, and that should be sufficient. But if you want to follow along, you are free to do so. So right now I'm defining a 2D NumPy array. So I hope you understand how this structure arose. So this is basically a list containing two lists. The first list contains 0, 1, 2, and the second list contains 3, 4, 5. And that gets arranged into a 2D structure, somewhat like this. Okay, I forgot comma over here. There. So that gets arranged into a 2D structure like that. Okay, so great. We now know what 2D arrays are. So just like in this picture, we see that 2D arrays are a grid of data, 2D grid of data. Similarly, over here, we have this 2D array being represented as a grid of data. So, for example, the first column of the first row contains 0, the second column of the first row contains 1, third column contains 2, and so on. So that's what 2D arrays are. Let's move on to 3D arrays, and this will really be what we will be focusing on in the IB workshop. I'll just let me actually write that down. So let's make a 3D array. Let's call it array 3D, and so since we have two nested brackets for 2D array, we'll have three nested brackets for 3D array, and let's initialize it with these values: 2, 3, 4, 5. That's the first row. Let's go on to the second row. Yep, that's 6, 7, 8, 9, 10, 11. That should work. Yeah. So what I basically did was this: I created a 3D array, and each row of the array contains, so the first row of the array contains this structure, and the second row of the array contains this structure. The first column of the array contains 0, 1, 6, 7. The second column contains 2, 3, 8, 9. third column 4, 5, 10, 11. So this is basically the structure of this 3D array. If I print it, oh, should probably just do it over here. If I print it, you can see that the first row contains 0, 1, 2, 3, 4, 5. The second row contains 6, 7, 8, 9, 10, 11. You can think of it. So the shape of this array, if you want to quickly see, you can see the shape of any NumPy array using this, and it will print out the shape for you. So the shape is 2, 3, 2. What this means is there are 2 rows, 3 columns, and 2 what would you call it? So if this was a 3D grid, there would be 2 cells in the x direction, 3 cells in the y direction, and 2 cells in the z direction. So it would be something like this. 2 cells in the x direction, 3 cells in the y direction, and 2 cells in the z direction. 3D grid of this sort. So yeah, so this NumPy array is basically a 3D grid of this shape. I hope everyone is following up till here. If there are any doubts up till here, please ask. Okay, so since there are no doubts, I'll proceed. Right, so let's move on to how we can index the arrays. So NumPy provides us with very powerful tools to index arrays, and if we use them cleverly, then we can do a lot of things in very small amount of code. So if you want to index a specific element of the array, let's say I want to index this element. How would we index that? To index this element, we will first need to go to the second row because it's in the second row. So since it's zero based indexing, we'll write 1, and then we need to go to the third column of the second row. So when you go to the third column of the second row, we have zero based indexing, so we write 2, and then we need to access the first element in that third column, in the last cell. So the first element would be 0. So this is how you access this specific element in this 3D array, as you can see. So a useful way of thinking about 3D arrays would be to visualize it as a 2D array, but with an additional list inside each grid cell. So let's say we have a 3D array with 2 elements in the z direction. So we should visualize a small list of 2 elements in each grid cell if you want to visualize it as a 2D array. So this can sometimes help just to wrap your head around the concept of 3D arrays. It helps in visualizing it. So yeah, that's how you index any specific element. Now let's look at how we can index multiple elements at the same time. So we have this operator that helps us access multiple elements at the same time. So if we just use the colon operator in the square bracket directly, then it will give us the entire array. It will just print the array as it is. It will give us the entire array. So how can we be more selective while using the colon operator? We can try something like this. So in this case, we see that we replaced the first index with a colon operator. So what it will basically do is it will keep the second and the third index. Okay. Yep. Okay. So it will basically keep the second and the third index the same, and it will vary the first index to all the possible values it can be, and it will create an array using all the possible values of the first index. So for example, we keep the second and the third index. So for example, in this case, our second index is 2, which is this vertical, the 4, 5 and 10, 11 block is 2, and 0 reduces it to 4 and 10. So if we keep the first index variable, so we should get 4 and 10 as output, and that's what we get, 4 and 10. It might be a little confusing, but just think of it like, if we keep the rest of the indices the same and vary the first index, what values can we reach? So in case of 10, if we vary the first index, we can reach 4, and only 4 and 10. So that is why we get 4 and 10, because the rest of the indices are fixed. Similarly, if we try this, so in this case, we can reach, we can't move inside this cell because we have that fixed, and we can't move up and down because we have that fixed over here. So all we can do is from 10 we can jump to 8, and we can jump to 6. So we have 6, 8, 10. That's what the output should be, and that is what it is. Great. So let's do one more. Yep. So I'll let you guys try now. Can you tell me what the output of this should be? You can also write it in the chat, or you could unmute and speak up. Okay, we have one answer. Right, a lot of answers are coming in. So, right, the answer is 10, 11. And why is that? So we keep the first index fixed, so we can't go up and down. We keep the second index fixed as well, so we can't jump from this cell to this cell to this cell. But we can keep the last index variable, so we can move inside this cell. So we have 10 and 11, and that is what the output is. Great. So I think most of us understand this concept. So let's keep moving on.
Sir, excuse me.
Yeah, what happened?
Sir, how are these elements arranged in the cubical form which you have drawn in the Microsoft whiteboard?
Oh,
so
okay.
What would be the order of the numbers in which they are placed, from top to bottom or from bottom to top?
There's no. So, are you concerned whether in the case of, let's say, 10, 11, whether 10 will be here and 11 will be here, or will it be the other way around? Are you concerned about that?
Yeah, exactly. Yes, sir. That's the case.
Okay, so in this case, the order doesn't really matter that much, because, so let's say if you start from this corner and you consider this the axis wherein the numbers will increase, then your 10 will be here and your 11 will be here. But if you consider this as your starting point, then your 10 will be here and 10 will be over here and 11 will be over here. So it doesn't really matter in, so it kind of depends on where you want to start counting from, and it's not really relevant to the, it's not really inbuilt into the structure of this 3D grid. It depends on where you start counting from. That is why I wanted you to imagine it as a 2D grid with small lists inside each cell. So in this case, there is no confusion. If you start counting from this side, and this is your increasing columns and this is your increasing rows, so this will be column 0, row 0, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. And inside, let's say, inside the 0th row and 5th column, we have no confusion as to which element is the first and second, if you imagine it like this, right?
Yes, sir. It's clear. Thank you.
Okay. Okay. So let's move on to, yep, let's move on to, sorry about that. Give me 1 second. Yes, sorry about that. So let's move on to thinking of images as ND arrays. All right, so let's first start with grayscale images. Let me just check if I'm not missing any point. Yep, I'm not. Great. Okay, let's start with grayscale images. So what is a grayscale image? Does anyone know? Can someone like, if you want to write in the chat, then that's fine. If you want to speak up, that's fine as well. All right. Okay. So grayscale images are basically images that so there's one answer that RGB values are all same between 0 to 255. Right. But let's not think in terms of RGB. Let's just think in terms of a single channel. So what I mean by grayscale image is more of a single channel image. There. Single channel images are, I'll just show you an example and then we can start from there. So the first step is to import Opencv, and this is how you import Opencv. You write import Cv2. I'm also going to import matplotlib pyplot as plt. So this we are going to use to show the images right inside the Jupyter notebook. You will understand more as we progress along. Okay, so now that we have imported Opencv and matplotlib, let's read this particular image. I want to read this image and I want to display it inside the Jupyter notebook. How do I do that? I'll call this image veggies, and yep, I'll call this image veggies gray, in fact, because I'm going to read it in grayscale. So this was a colored image that you just saw, but I'm going to read it in grayscale. To read images in grayscale, you can use this function from Opencv called Cv2 Imread. Just a second. Okay. Yeah. So this function takes in two arguments. The first argument being the name of the file which the image has, and the second argument is either 0 or it can be 1. So if you give the second argument as 0, it will read the image as a grayscale image, as a single channel image. And if you give it a argument of 1, it will read it as a color image. So let's for now give it an argument of 0. And now we have veggies gray. It contains the grayscale image of the photo that I just brought up on the screen, of this photo. Yeah, so I now want to view this image. Before viewing the image, let's just see what veggies gray looks like. If I just print it, what does it look like if I just print it? So if I just print it, veggies gray looks like a Numpy array, right? So if you scroll up and we look at this, it looks pretty similar, right? In fact, it is very similar. In fact, it is a 2D Numpy array. So grayscale images or single channel images are 2D Numpy arrays. And each cell of that Numpy array is a value between 0 to 255. Let me just explain it to you with an illustration. Right. So we know that images are made of pixels, right? We can. So if I open this image, yes. So if I open this image inside this image editor program, and I zoom in a lot, we can see that images are made of individual pixels. So in effect, you can already see the grid pattern in images. So this is the grid pattern that I have been talking about over here. So a grayscale image can be expressed as a 2D Numpy array. And how can it be expressed like that? So in this 2D Numpy array, each grid cell will have a specific value, and that value can range from 0 to 255. And the value that each grid cell has will determine the color of the pixel that the grid cell corresponds to. So for example, the very first grid cell determines the color of the very first pixel, and the next grid cell determines the color of the pixel next to it, and the next grid cell determines the color of the pixel next to that, and so on. So this is how images are stored in 2D Numpy arrays. It's really simple if you think about it. Yeah, and you can clearly see the 2D structure over here. So now I want to print this image in the form of an image, not in the form of an array. I want to visualize it. How do I do that? To visualize an image, you basically use this command. And cv2 dot weight key. So if you're looking at this the first time, this can seem like a lot, but it's really simple. It's what it's basically saying is that this function creates a new window called showing wedges and displays the wedges gray image in that window. And the wait key function is just a function that halts the execution of the program until the user presses any key. So it halts the execution of the program so that you can see the image. So if I run this, a new window popped up right over here, and if I click on that window, we can see that we have the grayscale wedges image on our screen, and the name of the window is showing wedges. So great, now we know how to display images, but we can do better. We don't want to, like, for the sake of this workshop and for the sake of this Jupyter notebook, I don't want to display the wedges image as a separate window. I want it to display right inside my Jupyter notebook. How do I do that? So let's close this. Let's close this window first. Okay. Well, I guess you have to use the X button to close it instead of pressing any key on the keyboard if you don't want it to hang. But either way, so if I want to display that image right inside my Jupyter notebook, how do I do that? So for that, we have this piece of code that displays this image right inside the Jupyter notebook. How this works is kind of out of the scope of this workshop, but it is really simple. It's a similar function. It even is named the same, but just for now, assume that this display function displays grayscale images right inside the Jupyter notebook. You don't need to worry about how it does that. You can read about PyPlot later on your own, but it doesn't really matter even if you don't know how this exactly works. So for Jupyter notebook, you can prefer using this function, and if you're writing a standalone Python script, then I usually prefer to use this function because it's really much simpler to use and much less code. So if I run this, I get an error, and oh right, so PLT is not defined. So since my kernel terminated, I'll need to run all of these cells again, and hopefully that should fix the problem. Close this. Great. So now so if I run this, I get the grayscale image right inside my Jupyter notebook. So that's basically what this function does. It just displays the image right inside the Jupyter notebook. Okay, so let's move on now. I see only 64 people have joined the meet, although okay, never mind, we can keep going. Okay, so we see that grayscale images are basically a grid of numbers ranging from 0 to 255. There is another way you can visualize a grid of numbers, and that way is to plot them in a 3D chart. So imagine that you have a 3D axis, and over here you have a grid. This is the x, this is the y, this is the x, this is the y, this is the z. And a way you can visualize a grid, a large grid of numbers, is by for each point in that grid you can plot the value stored inside that grid cell. So for the first grid cell, the value, let's say, is somewhere over here. For the second grid cell, the value is somewhere over here. For the third grid cell, it's somewhere over here, let's say. So you'll get a curve something like this, and if you plot that over multiple rows, you will get a surface. So basically, a grayscale image is a way to visualize a 3D surface. It might be a little confusing right now, but I'll show you the 3D surface version of this grayscale image. So for that, I'll just bring in some code. So again, this code is something that I wrote, and you don't really need to understand fully right now how it works. All you need to understand right now is that this code takes this photo and it draws a 3D plot for each pixel in the photo. And if I use this function on my veggies gray image, it will plot the veggies gray image in 3D. Now granted, it does take a little bit of time, but once it completes processing, it will show you the 3D plot of the veggies gray image. Yep, still processing. Oh yeah, there we go. So we got the 3D plot of the veggies gray image, and you can even see the small fruits over here that are high in brightness values. They got bumped up, and yeah, so like seeing this, you might get some idea of how grayscale images are basically surfaces. So it might help you think of images more as functions in two variables. Great. So another example of an image, of a grayscale image, that will help you visualize the 3D surface in much more clarity would be this one. So let's import this image called spot gray. Spot is basically this image that I have in my system. So I'm going to import this image, and I'm going to make a 3D plot of this image. And seeing the 3D plot of this image will probably help you visualize how images can be understood as a function of two variables. So I just copy pasted the image display code and replace the variable with spot gray. And if I run this, you see this is the image that we imported. And let's plot this image in 3D. So now you can see that like now you can really understand how images can be understood as functions. So in this image, if I copy this image to, let's say, so if I copy it over here, I enlarge it. So in this image, so something I forgot to mention was that the darker areas are considered, areas are low in like whatever value they're storing, and the brighter areas have a higher value. So this is a completely dark region, so this will have a value of 0, and this is as bright as it can be, so it will have a value of 255. And in between the value ranges from 0 to 255. So for example, somewhere over here it will be, let's say, 230. Somewhere over here it will be 200. Somewhere over here it will be, let's say, it will be 10. Over here it's 0. So in this way the value continuously ranges between 0 and 255. Can you guys mute yourself, please? Unless you have something to ask. All right. So, and that is expressed in the 3D plot of that image. So over here the value is 0, and as we approach the center the value slowly rises up to 255. So I think this will help you better appreciate images as functions in two variables. Okay, so let's move on from grayscale images and let's discuss about binary images. Okay, so does anyone know what binary images are? Oh, I see there are a lot of questions. Let me address those questions and then we can proceed. Also, if you feel like I'm not viewing the chat, then you can like unmute yourself and speak up. So what is the second argument in cv2.imread? In cv2.imread, let's see where it is. Right, so cv2.imread, the second argument is it basically tells us as to how do you want to read the image. If you specify 0 in the second argument, it reads the image as a grayscale, and if you specify 1, then it reads the image as like a color image, a multi-channel image, which we'll be discussing about in the next section. Does that answer your question? Am I audible? Okay, so if my explanation answers your question, then you can probably just react to your question, and I'll know that it answers your question. Someone is raising hand. Yes, Anirudh. Would you like to say something? Hello. Okay. Let's move on to the next question. So the next question is. Oh, I think it's the explanation of the above question. Okay. So the output of wait key. Right. So you can look that up. Actually, you can go to the Opencv documentation. Wait key. There. Yep, and you can search for the return value. It returns the code of the pressed key, or -1 if no key was pressed before this specified time had elapsed. So it basically returns whatever key you pressed. It returns I think it returns the Unicode value of that key, or it returns -1 if no key was pressed. So that's the output or the return value of wait key. What wait keys does is it adds delay to the program. If you specify a non-zero value in wait key, it will halt the program for that many milliseconds. And if you specify a zero value for wait key, it will halt the program indefinitely until you press a key. So yeah. Okay. What do the outputs signify in both pyplot and Opencv functions? Okay, so do you mean this image?
No, the return values that will, it's okay. It answered the question. Just answer the question. It's okay.
Okay. Okay. So can you also explain why Grayscale Images second is 2D Numpy Array? Okay. So let's say you have a 2D Numpy array. Where did the whiteboard go? Over here. Let's say about let's think about this array. Let's say this array has a value of 0 over here, 0 over here. I'm just filling in values at random. 5, 6, 7, 0, 0, 0, 1, 3, 0, 5, 7, 6, 7, 0, 0, 0, 0. Okay. So let's forget about this part. Let's say this is your 2D Numpy array. Now what if you started coloring the grid with, like, in proportion to the value that it holds? So let's say if it holds the value of 1, you would color it with a certain intensity of illumination. And then if it holds 3, you would color it with a darker intensity, like a higher intensity of illumination. If it holds 5, you would really color it with like a lot of intensity. If it holds 6, you would like fill it up. So you see how this is creating like a pixel structure, right? If you zoom out enough, this will look like a grayscale image. Does that satisfy your question? Like, does that answer your question, Swaroop? Okay, great. Next we have the 3D plot may not be continuous. Should we call it a surface? That's a very good question actually. So the 3D plot may not be continuous. So should we call it a surface? Right. Where did my Python notebook go? Over here. Right. So the 3D plot may not be continuous. It may not be. You're right. But so when we take images, we basically discretize what the camera is, like whatever image is projected onto the sensor of the camera, we discretize it into the pixels of the image. If you want to think of an image, you would probably want to think of it as an interpolation of values between those pixels. Because so this might be a little bit advanced to talk about right now, but if you let's say you want to scale the image, or if you want to rotate the image, then if you scale the image by 4, then 2 pixels which are like next to each other move apart, and there are more pixels in between them to fill. So how do you fill those pixels which you don't know the values for? So you basically interpolate between these 2 pixels, right? So once you consider interpolation in, like, along with the image, then you can call it a surface, because then it becomes a continuous thing. Does that answer your question?
Yes.
Okay. So how does the second argument in cv2.im show, that is 0, make the image grayscale? Does it take average value from 3 channels for each pixel, or max of the pixel intensity from the 3 channels? That's a great question actually. Why don't we go to the Opencv documentation and check this out. Opencv Imread. I believe you meant Imread, not Imshow. So okay, let's go to the Imread documentation. Yes, so we have, when using Imread grayscale, the codex internal grayscale conversion will be used. So they haven't really specified how they would convert it from Bgr to grayscale. Okay, maybe like it will be mentioned somewhere deep inside the documentation. You can probably figure that out if you want to dig deep into the documentation. But yeah, so the ways that you have mentioned are valid ways of converting RGB to BGR. You can take the average of the 3 channels, or you can select the maximum, or you can take the value of, convert it into Hsv color space and take the value. So those are valid ways of converting image to grayscale. Yes, okay, so that's probably a little bit advanced at this stage. Let's move on to binary images now. Okay, let's take this last question and then we'll move on. For 49, 40, 30, it's given 38, which is close to average. Okay, then it might be probably it might be the average. You can test it for yourself. Like you can create convert color does what? I haven't used. Oh, we have used convert color over here. Right. So we'll be talking about convert color in the next section. So don't worry about that right now. We'll come to that. What is the time right now? I think we have completed 1 hour, right? Okay. Cool. So let's talk about binary images. Does anyone know what binary images are? It's really simple actually. Binary images are basically grayscale images, but they can have only 2 values, either 0 or 1. Or they can have only 2 values, either 0 or 255. So images like those are binary images. So for example, I have this image called Eiffel in my system, and I'll read that and I'll show you what a binary image looks like. So I'm going to read it as a grayscale image. And I'm going to display it as a grayscale image. So I just copy pasted the display code over here. There's a type error.
Eiffel spelling is wrong.
Is it?
Eiffel.png.
Right. Thanks. So yes, so once we read this image and I show print this image, you can see that this image has only 2 colors, white and black. So this is basically what a binary image looks like. If I plot this image in 3D, you can also see ifl_bin. You can also see that like there are only two like you will see only two levels, like the ground level and the top level. So yeah, only two levels. There's a ground level which hasn't been plotted for like visualization purposes, and the top level which is also not been plotted for visualization purpose. So these like perfectly straight walls that you are seeing are the edges between the black pixels and the white pixels. All right, so that's basically what binary images are. I think that should be clear enough. Is there any doubt in this? Images whose pixel can have only two intensity values. Yes, you're right. So if there's if there's no doubt in this, then we'll probably move on to the next section. Great. So no doubt in binary images. So we'll be moving on to multi-channel images. So right, what are multi-channel images? Can someone tell me? Okay, I'll just let you know. So multi-channel images are images which have like more than one channels. Why would images need more than one channels? They would need more than one channels if they are color images. So color images have to color images can't be displayed with a single channel. You initially read the image as grayscale image. If it were a normal image, would it use any conversion factor, like taking any value greater than half as 1 and lower than half as 0 to change it to binary? Okay, so yes, that is possible. That is what we call thresholding, and that we'll be discussing in the like this today. We'll be discussing thresholding as well. So what you described is basically thresholding, and we'll be discussing that in the next section. Okay. Right. So back to multi-channel images. Multi-channel images are like images which have more than one channels, and they are like you need multi-channel images so that you can display like color images. So color images can't be displayed in a single channel image. They need multiple channels. For example, like the red channel, the green channel, the blue channel, if you have heard of RGB. So I'll just read a multi-channel image really quickly and I'll show you. So we'll go again with the veggies image. This time I'm not using the underscore gray to differentiate the variables. So veggies will be cv2.imread veggies.jpg, and this time notice that I use the second argument as 1. You can either use the second argument as 1 or you can just omit the argument and it assumes it to be 1 by default. So if I run that, now the veggies variable has the 3 channel image veggies.jpg unit. So let's just see that image showing veggies. And I shouldn't have run that. Why should I not have run that? It's because I forgot. it's because I forgot to write the cv2.wait key 0. So if you don't add cv2.wait key 0, your window will not show anything. It requires the wait key 0 to display anything to the window. Alright, so this should probably, so I'll have to run from the beginning to import cv2 and matplotlib.pyplot. And we quickly close that. So it will take a while to plot the veggies gray. So until then, let's discuss about multi-channel images. So multi-channel images, so this image typically is an RGB image, and so you might have guessed the 3 channels are red, green and blue. Right. Oh, it's taking a lot of time. Okay, there we go. It's plotting the Eiffel Tower now. Right, so the 3 channels in this image are red, green and blue. And you can see like it really, like you can see that it once we use 1 in the argument, we can have a colored image stored in the veggies variable. And so the PLT function for showing this right inside the Jupyter notebook is slightly different. It requires the use of convert color, and that just prints it in the Jupyter notebook. So you don't need to worry about the convert color right now. We'll be talking about color spaces in the next section. So we'll figure out what convert color is over there. Right now, all you need to understand is that this function lets you print the image right inside the Jupyter notebook. All right, so let's look at what veggies looks like. How is it stored in the NumPy format? So this looks like quite a big array, and it is. Let's break down what it is. So basically we have 3 square brackets. So that means it's a 3D array. So the first row contains, this has the first cell, this has the second cell, this has the third cell, and so on until this. The second row contains, this has the first cell, this has the second cell, this has the third cell, and so on until this. So it is basically like the 2D grid I asked you to imagine, wherein inside each grid we have a small list, and in this case, since we have 3 channels, we will imagine 3 components in each list. Can anyone guess what these 3 components will be? You don't need to guess, actually, you already know this, I think. Can someone write in the chat what the 3 components are? It's pretty easy, actually. The 3 components are, yep, the values of RGB, correct. So each cell represents a pixel, and each pixel has 3 values, R, G, and B. All right. So now we know what the image looks like in NumPy format. So okay, addressing your question, why is there a -1 in out25? Where is out25? Okay, so there's a -1 over here because we had a cv2.wait key 0, and then I closed the window, so it returned -1. we saw what cv2.wait key returns in the Opencv documentation, right? Yep. So that is why there is a -1 over there. All right, so let's move on. So this is what the veggies, excuse me, the veggies array look like. So I think you probably have a fair bit of understanding now of single channel, multi-channel, and grayscale images and binary images. If there's any doubt in how images are represented in NumPy format, then go ahead. You can ask your doubts right now. Why does RGB become Bgr in PyPlot? Oh, that's just because of convention. Like, so Opencv, when it reads an image, it stores the blue as the first channel, green as the second channel, and red as the third channel. So Opencv, so since we are using Opencv to read the image, once we have the image in NumPy format, the image looks something like this: Bgr, Bgr, something like this. And PyPlot assumes that the image has been stored as RGB. So when we plot an Opencv image in PyPlot, the colors look wrong. But that's just because of the convention that Opencv and PyPlot assume. So if you read an image from PyPlot and display from PyPlot, then it will not have that problem. If you read from PyPlot and display from PyPlot, I think it will not have that problem. And if you read from Opencv and display from Opencv, it will not have that problem. But if you try to read from Opencv and display into PyPlot, then you run into convention issues. So you have to do that conversion. I think that answers your question.
Yeah.
Okay. All right. So where were we? Yep. Okay, let's move on to. So this could be a fun activity if you guys have the setup right now. We are going to try to capture your webcam using Opencv. How do we do that? So we can do that by so first of all, we need to make a cam object that is of the type cv2.videoCapture. Capture. I think that's the spelling. Yep. And we are specifying 0 because we want to use your default webcam as the video capture device. Instead of 0, you could have written a path inside this function, and it would read that the file stored in that path. So it would read frames from a video file stored in that path. But since we are not specifying a path, we are specifying 0. It will read frames from your webcam. So, and I should not have. Let's just continue in this cell, and let's write cv2.wait key. So what I'm basically saying here is that run an infinite loop until I press spacebar. So until I press spacebar, it will keep running this loop. Inside this loop, I want to read a frame from my camera and store it in the frame variable. And now I want to see what the frame variable has stored inside it. So I'll use the webcam cap. So I'll just make a window called webcam capture and display the frame inside that window. And so because this is a while loop, it will keep running until I press spacebar. So it will keep on taking frames from my webcam and displaying it on the window until I press spacebar. So once I press spacebar, I just want to release the camera. Like I want to delete the memory allocated to the camera, and I also want to destroy all windows there. So what this basically does is once you stop this loop, it will destroy the webcam capture window and it will release the camera object. So let's try running this. For that, I will be switching off my webcam from Teams and I will be using that over here. So you see the star mark over here, it means that it's running. And over here, I think everyone can see the feed, right? Can you guys see the feed, camera feed?
Yeah.
Okay, great. So we have the camera feed over here. So now if I press spacebar, then cv2.wait key will return 32 and it will break out of the loop. So I pressed spacebar and it broke out of the loop and destroyed all windows and it released the cam. So that is basically how you capture your webcam using Opencv. And so if you have that frame, you can perform all sorts of operations in the frame. You can perform all sorts of operations perform IP on the frame, and then you can display that frame. Oh wow, we keep running that cell. Okay, so that's basically how you capture video from your webcam. And I will resume my webcam over here. So yeah, that was the first section of this workshop. We have 2 more sections today, and if you guys want a 10-minute break, you can have it, or otherwise we can continue. Let's just answer these questions really quickly. What does ret variable store? Okay, ret variables basically stores whether a frame was returned or not. So if there was no frame returned, then return will store false, and if there was a frame returned, then return will store true. And so that is what ret variable stores. So cam.read returns a tuple of values. It returns either it returns a true and a frame, or it returns a false and nothing. So that is what is the output of cam.read. Does that answers your question, right? Yeah. Okay, let's move on. Why cv2.wait key 1 here? Why 1? Okay. Right. So I told you earlier, right, that cv2.wait key basically induces delay in the program. So if I write cv2.wait key and inside the brackets I write x, it will introduce x milliseconds of delay. So if I want to run some program at, let's say, 30 fps, so inside the while loop I'll write cv2.wait key 1000 by 30. Yep. And that will let me run it at 30 fps. So basically I'll write cv2.wait key 33. right here I've written Cv2.wait key 1 so that like it does not take even a millisecond of waiting time. It like instantly moves on to the next statement. I've done that just to like, I don't want Cv2.wait key to be the code segment that slows my code down. I want it to run at the fastest speed, so that is why I've written 1. Like there's no smaller value than 1 that you can put there. If you put 0, it will halt indefinitely until you press a key. So that's that. I hope that answers your question. Yep. Okay. Great. So do you guys want a 10-minute break, or like should we continue? Okay, let's just do a poll. All those in favor of break, raise your hands. Let's try that as well. 13, 14, 18. 27 out of 55, 30. Okay, we already crossed the majority. Fine, we'll have a 10-minute break and then we'll return. See you in 10 minutes. Okay, yeah, let's continue with the workshop. So this one should be okay. So let's now go ahead and discuss about color spaces. There. I'm audible, right?
Yes, but you're not sharing any screen.
Oh,
Screen is not sharing.
yes. Thank you for reminding me. It's visible now.
It is.
Okay. All right. So yeah, let's now discuss about color spaces. So we have already come across one color space, which is the Bgr color space, and in that you can probably guess the B stands for blue, the G stands for green, and the R stands for red. So there is a function in Opencv using which you can split the channels of an image. So let's say if an image has 3 channels, you can split them into individual grayscale images. So before looking at that function, let us like properly understand what the Bgr color space is. Let's look at this diagram over here. So the cube that you're seeing in front of you is the RGB cube. So like you can see that on this end, like in this entire row, in fact in this entire face on this side of the cube, the value of blue is 0. And on this side of the cube, the value of blue is the maximum that it can be, 255 in this case. Similarly, the value of green on this face is 255 and the value of green on this face is 0. Wow, those are really odd shaped rhombuses, but okay. So similarly with red, the value of red on this plane is 0 and the one in the front plane is 255. So this is the RGB cube. I think I haven't enabled my face cam. Now it is enabled. So that's the RGB cube. If you so on this end we have 255 of red, green and blue. All are 255, all are at its maximum. So when all three RGB are at maximum value, then we get white color. And right opposite to this vertex, somewhere over here, would be the point where R, G and B would be 0, and that will be the black, like it will be the vertex which would have the point which would have a black color. So black means RGB are 0, white means RGB are 255, and everything in between is basically a combination of RG and B. So over here B and G are maximum, and that gives us a cyan color. Over here I think it's so over here blue is not there, green is at its maximum and red is not there, so this is just green. Over here red and green are at maximum. Over here red and blue are at maximum. Over here it's only red. Over here it's only blue. And yep, that's that. So I hope this gives you a little bit of an idea of what this RGB cube is. So some things that you can take away from here are that yellow is made up of high red, high green and low blue. Pink or purple is made of high red, low green and high blue. It's somewhat of a basic color theory knowledge. Then we have, so this is additive colors that I'm talking about. This kind of high red and high blue gives us purple is called an additive color space. There's another thing called subtractive color space, which, if I'm not wrong, cyan, magenta, yellow, black color space is. We'll be talking about that later on. But this color space is an additive color space. So in here, if you add R and B, it gives you purple. Red and blue gives you purple. So it's somewhat of a color space which mimics how light behaves. So for example, if you have a red color light and if you have a blue color light, then like if you have a red color torch and a blue color torch, then where their regions intersect will form a purple color. It's somewhat of that additive nature. All right, let's just get rid of these, and we have, and this we have, so we have cyan is high in, so low in red, high in green and high in blue. So you could also call this as magenta. So you can see how RGB and CMYK color spaces are related. Although I haven't talked about CMYK color space, but if you have already heard about it, then you can see how RGB and CMYK are related. If you haven't heard about CMYK, don't worry about it. We'll talk about it later on. Right now, all you need to know is that like yellow is made up of red and green, magenta is made up of red and blue, cyan is made up of red and blue. Sorry, green and blue. So that's that. Yep. So that was basically what I had to talk about Bgr Color Space. Let's now back to the Jupyter notebook, and let's see how we can split a multi-channel image into 3 single-channel images. So we do that by specifying b. So we have this function called cv2.split, and we supply it the image that we want to split, and it returns the first, second, and third channel in that order. So in Opencv, the first channel is blue, the second channel is green, and the third channel is red. So it returns those channels in that order. So now if we plot the blue channel, we get this. If we plot the green channel next to it, let's plot also the red channel next to it. So I'm plotting the blue, green, and red channel in that order. So we get this. One sec. Right. So we get this these 3 images. So just to give you a little bit of intuition, if we look at the color image, we see that the right side is purple colored, so it should be rich in blue. The left side is somewhat greenish, cyanish color, so it should be rich in blue as well. The middle portion, however, is yellowish and reddish, so that should be somewhat devoid of blue. And that is what we actually see. So the left side is somewhat rich in blue, the right side is somewhat rich in blue, and the center portion is devoid of blue. Similarly, the cyan, the green, and the yellows they are rich in green, while the red and the purple are like devoid of green. Like we see here, the red region and the purple region have less green, and these regions are much more greener because this is the green channel that we are seeing. And in the red channel, you can clearly see a lot of red in the middle of the region, in the middle of the image, because the middle region is composed of orange, yellow, and red colors. So red has a lot of prevalence there. So that's a little bit of intuition as to like why the channels look like the way they are. So yeah, that's basically the Bgr color space. Let's try to all right, so there's this program called GIMP, and it's a free image manipulation program, and it lets you like manipulate images, perform image processing like very easily. Like it's very easy to perform image processing using this program. So let's try fiddling around with this program and see what we can learn more about the color spaces. So here we have the veggies image, we can go to colors, and then we can go to components, and then we can go to decompose. What this basically does is that it will ask you what color space do you want to decompose this image into. Right now we are looking at the RGB color space, so we'll select RGB and click OK. And in a separate tab, it will decompose the veggies image into 3 layers: the red, green, and blue. So right now we are looking at the red layer. If we hide it, we are looking at the green layer, and if we hide it, we are looking at the blue layer, which you will see is very similar to, in fact, it's exactly the same as to what we generated using Opencv. So the blue layer has more blue in the left and right sides, like we had in Opencv. The green had more green on the greens and in the oranges, and less in the reds and blues. And the red layer has a lot of red in the middle, in the oranges and reds, and lesser in the greens and blues. So that's what we saw in the Opencv decomposition as well. Right. We can also look at this mono mixer. What mono mixer does is it takes the red channel, it takes the green channel, and it takes the blue channel, like we had in our Opencv code. Where did it go? We have these 3 channels, B, G, and R. Now what it does is that it divides the B channel, the whole B image by 3. It divides the whole G image then by 3, and it divides the whole R image by 3. What do I mean by dividing by 3? It goes to each pixel and it divides the value of each pixel by 3. So if this pixel was, let's say, 33, it will rewrite this pixel as 11, and then it adds all of them up. So in effect, we are taking the average of all these 3 images. So if we take the average of the blue, red, and green channel, we end up with this grayscale image. So taking the average of the blue, red, and green channels is a very common way of producing a grayscale image. So that is basically what is happening over here. Let me quickly have a look at the time. It's 10, so that's fine. We have time. But what's more useful about this mono mixer is that you can change the coefficients by which the channels are being multiplied. So currently they are being multiplied by 1/3 or 0.33. You can change those coefficients and you can see the change in the image in real time. So if I start decreasing the reds in the grayscale image, you can see that the regions where the red was most prominent start disappearing first, and then it spreads to the regions where red was less prominent. Similarly, if I start decreasing green, it vanishes first from the regions that were more prominent in green, and then it spreads to the regions that were less prominent. Similarly, if I start decreasing blue, let me keep this back to 0.3, you can see that it decreases first from the regions that were most prominent in blue, and even if I go way down, even if I go way down, the regions in the middle still don't vanish because they have very little blue in them. So this is something very useful that you can play around with, and I think it would be a very good exercise if you try to implement this mono mixer using Opencv code. So that will be a very good exercise, and it will also help you learn how to use sliders in Opencv, and it will also be a very intuition building exercise for you. So I strongly recommend that you take some time, not right now, after the workshop, you find out, take some time and try to implement this on your own. So yep, that was the mono mixer for the Bgr color space. We can now look at, let me see. All right, so let's look at the convert color function that someone was asking. What is convert color? Convert color basically converts between color spaces. So let's say we have the Rgb color space and Bgr color space. They're not much different. They are just like a change of axis, but still, like, we can consider them as different color spaces. So what convert color allows you to do is, if you have an image in Bgr, it will allow you to convert it from Bgr to Rgb. And if you have an image in Rgb, it will allow you to convert from Rgb to Bgr. If you have an image in some other color space, let's say color space XYZ, this is just something that I'm making up, you can convert from RGB to XYZ and vice versa. So how do you use convert color? It's pretty simple actually. You just write Cv2 dot convert color, and inside the convert color, I'll just quickly copy the syntax from here. Inside the convert color, you write the name of the image, and you write what type of conversion do you want to do. So if the image is originally Bgr and you want to convert it to Rgb, you will write Cv2 dot in capitals color underscore Bgr to Rgb. So the output of the convert color will be an image. Let's say Rgb veggies, and the Rgb veggies will have the first channel as red, second channel as green, and third channel as blue. So this is basically how you use convert color. Right. So I hope there is no doubt up till now. Let me check the chat really quickly. Okay, there are some things in the chat. What's the name of the software? Okay, the name of the software is GIMP, GNU Image Manipulation Program. Yep. So the next question is, I'm having some trouble with using Opencv on Jupyter Notebook and VS Code on M1 Mac. However, the package is installed and is working on the terminal. I have attached a screenshot. Do you know how I can solve it? Okay. The troubleshooting and debugging questions we can take up after the workshop maybe, or like you can mail me or message me and I can help you with that. Let's keep this time for workshop related questions. What if we just add the 3 channels instead of taking the average? Pixel value exceeds 255 at some points, right? I don't have the GIMP software to check. Yes, you're right. Pixel value will increase to 55. So in that case, what usually happens is that if pixel value exceeds 255, I think what GIMP does is that it takes the minimum of 255 and the pixel value if it exceeds 255. So basically it clips it at 255. So if the let's say if the pixel value is not 255, it remains the pixel value. But if it exceeds 255, it just reduces it to 255. All right. Yes, so let's proceed to the next color space. I hope there are no doubts with the Bgr color space. If there are any doubts, then please write in the chat. Okay, okay, no doubts. So we'll move on to the Hsv color space. Right. Um, oh. So the Hsv color space. Has anyone heard of the Hsv color space? Or can someone tell me what the I'll not write. Can someone tell me what the H, S, and V stand for in the Hsv color space?
S stands for saturation,
Mm-hmm.
and I don't remember the rest.
Yep. So H stands for hue. I keep right. H stands for hue. S stands for saturation, as you said, and V stands for value. So HSV, hue, saturation, value. How is HSV different from RGB, or how can we? Yep, let's look at how HSV is different from RGB. We have, let me clear this up. Yep. And let me clear this. Yep. Okay. So we have this RGB color space represented as represented in the form of a cube, because that is basically what it is. It like the RGB are like they are orthogonal to each other, and yeah, so cube is the best representation for the RGB color space. But for the HSV color space, the best representation is actually a cylinder, or sometimes even a cone. So let's look at how we can wrap our heads around the Hsv color space. What you see over here is a hue wheel. So it starts at like 0 degree, and 0 degree is red. At 120 degrees is green, and at 270 degrees is blue, and in between, like at that's 60 degree, this is yellow. At 90 degree we have cyan, and at this is minus 45. What is that? How is this 130? Oh, all right. Yep. So in fact, this wheel that you see over here, this doesn't span a 360 degree. This doesn't span a 360 degree. It spans a 180 degree. This can be a little confusing, but bear with me. So this wheel spans 180 degrees. So whatever values that you're seeing, they are just like halved. So let's not think of it in terms of degrees anymore. Let's just think of it in terms of values. So at 0 is red, at 30 is yellow, at 60 is green. Wow. At 60 is green. At 90 we have cyan. At this is 120 we have blue. At 100 and this should be wait a second. So
I think it should be a magenta.
Yep, this should be a magenta.
Magenta.
Yep. And then we come back to 180 degrees and we get to red. So we'll come to saturation and value in a bit. Apurv is asking a question about it. We'll come to that in a bit. So right now this wheel only represents the hue, and so if we unwrap this, at 0 we'll have red, at 30 we'll have yellow, at 60 we'll have green, at 90 we'll have cyan, at 120 we'll have blue, at 150 we'll have magenta, and at 180 we'll have red. Yep. So you can see that why it is represented as a wheel, because the hue at 0 and the hue at 180 is the same. So it really should be represented as a wheel. But if you want to think of it in linear terms, you can think of it like this. So I think like we have a fair bit of intuition about hue. So let's move on to the saturation and value. How do we make sense of those? So consider, so I'll explain to you what saturation and value are in simple words. Saturation is basically how much color do you have. A low saturation means that we don't have a lot of tint to the color. We are tending more towards a black and white color than a tinted color. And a high saturation means that we have a tint of like a very tinted color. So for example, a high saturation blue would look like a blue, but a low saturation blue, you would be like, it would be very hard to tell whether it is blue or not. So it will be very hard to tell. So like you can see in the cross section over here, this you can very easily tell that it is a blue. But as you go down the saturation, you start to lose the tint and you move slowly towards the grayer colors. So that is basically what saturation is. Value is how bright the colors are. If the value is high, then we have very popping colors, like very bright and popping colors. And if the value is low, then we have dark colors. If the value is 0, then we have black. Similarly, if the saturation is 0, then we basically have grayscale. We don't have any color. We don't have any tint. So these are the three three sliders, you could say, that govern this color space: hue, saturation, and value. And you can really make all possible colors using this. Like all the possible colors that you could have made using RGB, you can make using hue, saturation, value. Okay. Daksh Kocher writes 240. Was it when I like mislabeled the color wheel? Was it back then?
Yes.
Okay. Okay. So Apoorv writes what color will be there at 0 saturation and 0 value. So at 0 saturation, we will have a color which is between either white or black. There is no, like, it will only be a grayscale color if you have 0 saturation. And 0 value means that we cannot have white. We will, like, 0 value means that we'll have black. So at 0 saturation, at 0 value, no matter whatever, like your hue doesn't matter here. Like your hue can be any value. At 0 saturation, at 0 value, you will have black. That is why sometimes the Hsv is represented as a cone as well, because at 0 saturation and 0 value, your hue doesn't matter. At 0 saturation and 0 value, you can only have black. That's a single point. So, yep, I hope that answers your question, Apoorv. Okay. Aman asks, can you please explain saturation again? All right. So saturation is the amount of tint in your image. Amount of, yes. So if so, the best way I can explain saturation is if you, I'll just fire up GIMP, and inside this, I'll go to saturation, and so what this basically does is it decreases the saturation of the entire image. So as I decrease saturation, look what happens to the image. It will become more and more grayscale. So at this point, it is completely grayscale. And if I keep increasing it, so at like double the saturation, it looks very vibrant. So all the colors, so all the colors are like very tinted. So they are very popping. But at like, so that's basically how you can have an intuition about saturation. So once you have 0 saturation, your hue doesn't matter again. So once you have 0 saturation, your hue has no effect. All you are left with is the value, as you can see in the diagram. Once you have like 0 saturation, the hue doesn't matter, only the value matters. So what you're seeing over here is just the value of the image. And yeah, even at, so once you have 0 value, even your saturation doesn't matter. So once your value is 0, neither does your saturation matter, nor does your hue matter. At value 0, you will always have black. I hope this was clear. I'm reading some questions now. So can we assume each color space as basis vector of the total color space, just like the coordinate system? Hsv will be spherical coordinate system and Rgb Cmy as a rectangular coordinate system. Yes, you can do that. Yes, so the Rgb has a rectangular coordinate system. You're correct on that. And in the Hsv, I'm not sure if you can assume like a cylindrical coordinate system here, because of how when you have 0 value, neither does the saturation matter nor does the hue matter. So I'm not sure about Hsv, but in Rgb you can definitely assume it as the basis vector of a rectangular coordinate system. Yep. So Cmy, I'm not sure again, because Cmy is a subtractive color space. So I I'm not sure like how the basis vectors would look like in that coordinate system. Will they be rectangular or not? But in the case of RGB, yes, you can definitely do that. Nice question. So the next question is, what does saturation change translate into in RGB terms? Like, does it mean decreasing, increasing, all three values proportionally? Oh, that's a great question actually. So, it does not. I can give you an intuition for that, but uh, so there are exact formulas for converting from one color space to the other color space. So there's an exact formula for converting from RGB to HSV and from HSV to RGB. I won't tell you the formula, you can look that up, but what I will tell you is a basic intuition as to what saturation is in terms of RGB color space. So in terms of RGB color space, if you have, let's say, um, let's say this is the R value, this is the B value, RG value, this is the B value. So if the R value is high, if the G value is high, and if the B value is high, then you have white, which is the zero saturation. So let's look at another case. If the R value is low, if the G value is low, if the B value is low, then you have somewhat of a black color, which is again zero saturation. So, or it could be like low value as well, but if they are like mostly equal, then it's zero saturation. So saturation can be thought of as how much difference there is between RG and B. So if the difference between RG and B rises, the saturation rises. You can think of it somewhat like that. Of course, like you can look at the exact formula and then you will have a much better idea. But this is a rough intuition of how it works. So let's say we have a lot of red, no G and no B. That will be a very saturated red. Similarly, a lot of green, no red, no blue, a very saturated green. A lot of red, a lot of blue, but no green, will be a very saturated magenta. So that's a little bit of intuition on that. I hope. Yep. Okay, great. Are there any more questions on color spaces? Check the time. Right. Okay, so if there are no more questions, then we can proceed on to the next section. Let me quickly check if I'm missing something. Sorry. All right, so yeah, this is the one. Yep. So let's now split the veggies image into H, S, and V channels instead of B, G, and R. How do we do that? So let's make a new image called HSV veggies, and that image will store the converted veggies image. What will the veggies be converted to? It will be converted to an HSV image from a Bgr image, right? So the Hsv veggies has the veggies image in the form of hue saturation value. So the first channel of Hsv veggies will be hue, second channel will be saturation, and third channel will be value. Now if we use the split function to decompose the Hsv veggies into Hs and V, we'll obtain something like this. Now we want to show each of these channels. Right, let's just do that. We want to show each of these channels, just like we displayed each of these channels over here. We want to show each of these channels over here. One thing to keep in mind is that the hue value varies only from 0 to 180. So I'll change the maximum value to 180 over here. And now I'll display it. So this is what the hue channel looks like. This is what the saturation channel looks like. And this is what the value channel looks like. You can see that the value channel is like a very good grayscale image that we can use. So the value is often used as a grayscale image. And the hue and the saturation channel looks like this. You can see that this image has a lot of saturation in it, and you can also see that directly from the image. So it has very popping colors, very vibrant colors. That is why the saturation is high in this image. And the hue image, when viewed in grayscale, it doesn't really make a lot of sense, because it is we are basically trying to unwrap a circular structure into a linear grayscale value. But there's a feature in PLT IMShow that you can utilize to map this onto an Hsv color map. So basically what it does is that it takes the grayscale value and it maps it, it replaces it with the color, with the most saturated color of that hue. So let's say what you're basically going to see right now is any point in the hue saturation wheel will be pushed to the maximum saturation and value that it can possibly be pushed to. This point will be pushed to here, this point will be pushed to here, this point will be pushed to here. So all we'll be seeing will be this outer rim or this color wheel of hue in this image once we run this. So I'll just run this so you can get a better idea of what I'm saying. So once you run this, you can see that we basically boosted the saturation and value of the image to full and only let the hue dictate what the image looks like. And this is what you get. So you can see the greens have a green hue, the oranges have the yellowish hue, orangish hue, and the reds have a red hue. So it basically gives you an intuition of what the hue channel looks like. Are there any questions here? Can we say there are infinite color spaces? That's an interesting question. I think you can say that, yeah, but not all of them are useful. You can obviously just this you can take the, let's say you have the Rgb color space, and you just go ahead and define a new basis vector. You just take 3 non-linear vectors and say that these will be my basis for a new color space. You can always do that, but they are not the most useful, because in this case they are not orthogonal. So the more interesting question to ask would be, I think, the more interesting question to ask would be, why is the red, green, and blue colors, like why are they orthogonal to each other? Like that should be the more interesting question that like you should be asking. Um, I'll let you think about that. Um, and if you figure it out by the end of the workshop, by the end of this session, then add in the chat box. And if you don't remind me, I'll tell you why red, green, and blue are orthogonal to each other. All right. Can there be Hsv value arrays as well? Right, but the question is why are they linearly independent? Uh, yeah, sorry. Venkatasai said that maybe they are linearly independent, but that is the like that's exactly what is being asked. Like, why are they linearly independent? Um, why only red, blue, and green are linearly independent? Why not, let's say, red, yellow, and blue?
Hello.
Hello.
So I might have a possible solution, but I don't know if it's complete or not. Red, green, and blue. I mean, when blue and green is mixed and then it mixed with red, what you get is black, that is zero. Or in other way, we can say that green and blue, when added, give the complementary color of red, which is cyan.
Okay.
So it's like addition of vectors, and the total of the vectors turns out to be zero. So I guess they can form the primary basis. If we consider the Hue as the
you could say that. I think there is a more fundamental reason, and if I'm not wrong, then maybe we cannot split those colors using a prism. I don't think so. Like, why not? Like, we have Bgr, right? Like, we have several colors in those. So why red, blue, and green? So I think like what the main reason is for red, blue, and green to be linearly independent, it has to do with so I'll have to fact check on this, but if I'm not wrong, and you guys also fact check after the workshop, but if I'm not wrong, then it is because of the biology of our eyes, because our eyes have the red, blue, and green cones, which are sensitive to the red spectrum, blue spectrum, and green spectrum. And so because they like we have three independent cones for the red, blue, and green uh, spectra of light, so that is why we have linear independence among those three colors. And like that, and the combination of those colors to form more colors, that follows from this fact that we have independent cones for those spectra. um, yeah Someone fact check me on that, and maybe we can discuss it at the end of the workshop. All right. Can you scroll up a bit? Wait a second. I'll do that. Can there be Hsv value arrays as well? What do you mean, Aryan? I'm not fully sure what your question means. Oh, I think someone posted. I want to be here at the real primary color Rgb or RYB, as I got some discussion about it. Okay. Yep. So you guys should go and check out the link that Venkatasai Saran posted, and it seems interesting. Okay, Aryan says like the numeric values for the three parameters. I should probably bring this over here. Right. So like the numeric values for the three parameters of for the image. Okay, so maybe you're talking about this channel, is it? If you have a mic, like you can speak up and like we can have a better discussion. Hello? Um, Numeric values for 3 parameters for the image. Let me just wrap my head around this question. Can there be Hsv value arrays as well? Yes, there definitely can be Hsv value arrays, as I have just shown you. In fact, let me just like, print them out for you, and then you can like it will be much more clear to you as to what they look like. So the H array, the Hue array looks like this. It's a 2D array. As you can see, it's a grayscale image. The S array looks like this. It's also a 2D array and it's a grayscale image. And the V array looks like this. It's also a 2D array. It's a grayscale image. And these images are plotted over here.
So, like you said, the H is also that grayscale 2D array grayscale image, but like when you use the HSV CMap for plotting, then we could see the color image. So,
Yep.
like that part I couldn't understand. Like
Oh,
we are having the grayscale image values in the array, but like we could get this colored image.
yes, that
Is
is
it correct?
because so what I'm basically doing is I'm reading the value of hue, and if the value is, let's say, if I read a value of 10, then I make a new image with RGB colors, and I fill the RGB color with the corresponding fully saturated full value uh,
Oh, okay. The
color.
corresponding hue and the rest will be maxed out.
Yes.
Okay.
Yep.
Okay.
So that is what this get CMap. That is what this argument does. If I replace this with CMap gray, it will just show you the raw hue um, image. So again, you can look into plt.imshow later on your own. This is not really the scope of this workshop. But yeah, this looked like an interesting image. It also built some intuition into HSV. That is why I decided to keep this in the notebook. All right, so many questions. You get pink tint with blue and red. Who was this? What was this the answer to? We can mix. Okay, Kalyan. All right, so I think we are done with all the questions. I think we can move ahead. So that is what HSV looks like. I hope you got some intuition as to how hue, saturation, and value looks like. Let's delete this cell. Let's delete this cell. Let's delete this cell. Okay. Just before moving on, I think it's worth looking at how GIMP handles with hue saturation value. So I highly recommend that you download this program and play around with it, because like you can get a lot of intuition into image processing using this program. So again, I'm going into colors, components, and decompose. And this time, instead of selecting RGB, I will select HSV and click on OK. And you can see the image that we get is the like decomposed version of the colored image. So the layer that we are viewing right now is the hue layer, and you can see a lot of artifacts over here. Can someone tell me why we have so many artifacts, so many jagged edges? Even though in this image it looks pretty smooth, right? Like the hue is pretty smooth, it's all red. Why do we have so many jagged edges over here? It's not sunlight variation, because sunlight variation would probably affect the value, not the hue. So why do we have such artifacts. Like, think in terms of hue. Like, hue is not a linear thing. Like, it's a circular scale. So think in those directions. Yep, 0 and 180, correct. So this region is red, and its hue would, let's go back to the wheel. Its hue would either be positive, like somewhat around 0, 5, 10, somewhat like that, or it could be 180, 170, something like that. Yep, almost perfectly pure color. So um, where did the so let's say if you were somewhere over here, somewhere over here, this region has like positive hue, like some hues of like 1 or 2, and like you move just a little bit and the hue becomes 179 or 180, even though they look pretty continuous, but their values vary by a difference of 180. That is why we have like so many artifacts over here. So this boundary, for example, the value jumped from 0 to 180. That is why we have so many artifacts. And you will see that the artifacts only occur in the regions where we have a lot of red. In the regions of green, in the regions of blue, we don't have so many artifacts. So that is the reason. So like keep this in mind, slightly important, because we'll be using this for thresholding, like in using this concept for thresholding later on. All right, so that was the hue saturation value color space. For further reading, I would suggest you guys check out these links. Check out CMYK, cyan, magenta, yellow, black. HSL, which is hue saturation lightness, which is lightness is similar to value, but it has a slightly different fall off, I think. So, and there is this color space called lab. So I think you should go ahead and read about these on your own. And we'll mostly be using Hsv Color Space and Rgb and Bgr Color Space for the purpose of this workshop. So you don't need to worry about these color spaces for the moment. But I suggest you go and read about these in your own time. Yep. So with this, we come to the end of the color space section. We have one more section called thresholding. If you guys want a 5-minute break, we can come back after a 5-minute break and continue with the thresholding section. Do you guys want a 5-minute break by a show of hands? Oh, I see. We have... Oh, we don't have a lot of hands. Okay. In that case, let's just take a 1-minute break. I'll drink some water and I'll get back. Okay, great. I'll be back in a minute. All right, so let's start with thresholding. In fact, we will start with binary thresholding. Okay, so sorry, my screen is visible, right? And my voice is audible.
Yes.
All right. Uh, so we have. So let's just bring up that image of the spot that we had, the spot gray image. Let's just bring that up once again. This is the image I was talking about. So you see that this image we have. Sorry, I think I made the diagram. Yep, over here. So in this image we have uh, 0 values everywhere there is black, so all of this is 0. And once we like hit the border of this diffuse circle, we slowly start increasing in value. So for example, over here would be like somewhere a value of 1, over here somewhere a value of 10, like this would be probably 50, probably 100, 150, something like that, 200, 250, 256, roughly. So the value like increases gradually, right? So let's say that I were to give you this image, and I were to ask you to find all the points, all the pixels that have a value of more than 150. So what would you like? How would you figure that out? Like over here, what would the shape of the resulting image, like resulting thing be? Like my question is, color all the pixels that have a value of greater than 150 to be perfectly white, and color all pixels that have a value less than or equal to 150 to be perfectly black. What will the output be? Oh, I think someone's writing the answer in the chat. Let's look at it. Right, the answer would be a circle. It would be a white disk with radius at the 150 mark. Correct. So this is the 150 mark. We draw a disk around it, since the entire contour would have a value of 150, and inside that contour all the pixels will be greater than 150, since the value is increasing, and outside the contour all the pixels will be less than 150, so all of those will be black and all of these inside the contour will be white. All right, so this is what we call binary thresholding. What is it exactly again? So we take a threshold, let's say t, and all the pixels that are uh, greater than t, we color them a certain value, and all the pixels that are less than t, we color them in a different manner. So this is what binary thresholding is. All right, so let's go back to the Jupyter notebook and let's write. All right, so like what do you think should be the algorithm for this? Like what would be the algorithm for implementing this? It's pretty simple, right? Like it's like a common sense question.
Shall we iterate through every pixel and we then perform the desired operation?
Yep. Yep. So you could use a binary operator for the array, but for like implementing that operator, you would have to iterate through all the pixels and color them based on this condition. So it's basically the same thing. So list comprehension. Could you elaborate, Aryan? All right. Aryan, am I audible to you?
Yes, like that we do this thing in Python and lists that we can write some kind of, it's like it will be similar to the loop only, I guess.
Right. So right. So basically, the gist of implementing thresholding is you iterate through all the pixels and set their value based on the comparison. Right. So I would suggest you to, like, after the workshop, if you find time, try implementing the threshold function. Like try implementing a threshold function yourself. Right now I'll be discussing about the threshold function from Opencv. So let's go back to the Jupyter notebook. So the threshold function from Opencv looks something like this: cv2.threshold, and we input the name of the image that we want to threshold. So in this case it is spot gray. We input the value of the threshold. In our case it was 150, and we input what we want to color the pixels which are greater than the threshold. So for all the pixels that are greater than the threshold, what color do we want them to be? So let's say 255, we want to color them all white, and we write. So now there are different kinds of thresholds. The one that I talked about right now is known as cv2.thresh binary. So this is the kind of thresholding that I talked about just now. So what this function would do is it would threshold the spot gray image on the 150 mark and color all the pixels that are above the 150 mark. It would color them with the value of 255. And how do we so the output is of the format, is of the format red spot thresh bin. So I'll call the output image spot thresh bin, because it is a binary threshold of the spot image, and return value just stores true or false based on like the success of the threshold operation. So now I want to view the spot thresh bin image. So to view the image, I'll just use the command that we have been using till now. It's this command, spot thresh bin, and like you get the image that you expect to get. You get the disk, the white circular disk, and the rest of the region is black. So this is the kind of threshold that we talked about just now. So what if we instead of doing greater than 150 white, we do greater than 150, we color all the pixels greater than 150 black and all the pixels less than 150 white. What if we do that? Then like what will the output be? Can you guys write in the chat, or you can speak up? We have only mentioned the greater than 150, but we also got for less than 150. Yes. So let's look at the. Okay, I'll answer Apoorv's question first. Contrast of the image. I think you meant the inverse of the image, and yep, that's right. So we'll get a white region all around, and inside the disk will be dark. So so that is what we will get over here if instead of doing thresh binary, we do a thresh binary inverse. Let me store this in a different variable, thresh binary inverse. Then what we will get is the inverse of the threshold threshold that we performed above. Thresh binary inverse. So let's run this and see, we have the inverse of this image inverted. Right. Also, we have so just to give you an intuition, we can try like playing with this value. Like if we decrease the value to from 150 to 100, what do you think will be the effect on the radius of the disk? Right, the radius of the disk increases because we will because the 100 mark would come like much farther out, so we'll have a bigger disk. So that's basically why the radius of the disk increases. And similarly over here. Now to answer Venkatasai's question, we have only mentioned greater than 150, but we also got for less than 150. Do you mean like for this argument or for this argument? Which argument are you confused about?
Yeah, I mean for the second argument. So
okay.
Spot gray 100 and 255. We replace the values of greater than 150 with 255, but we are not concerned about for less than 150.
Right. I think it takes 0 by default, but just to confirm, let's look at the threshold Opencv documentation. So you should get into habit of looking up the documentation for any library that you're using. It will so if you're in the habit of looking up documentation, you will like save yourself a lot of time if you know how to read documentation. So we have let's see, this is a tutorial. Someone wants to join. This is all right, maybe we can go over here. Right, so we have the threshold function and we have the input array, the output array. This is a C++ version. In the Python version we have the source, the thresh, the maxval. So what does the maxval do? Maxval is the maximum value to use with the thresh binary and thresh binary inverse thresholding types. So if I reduce where is it? Oh, it's in this tab itself. So if I reduce this value, let's say I make it 150, we get a grayer image. So that's for sure that this value represents the value that we need to color the pixels that have greater than the threshold. The pixels that are greater than the threshold has to be colored with this value. That's for sure. So for the pixels that are lesser than the threshold, I think those are colored with 0 by default. So it assumes that you have to you want to color with this value, whichever pixels qualify, and the rest will be 0. So even in this case, if I change this to 150, the pixels which are white will become a little grayer, but the pixels which are black will stay black, is what I think. Yep. So the pixels which don't qualify the threshold will just remain black. Does that answer your question? Yep. All right. Okay. So this was binary thresholding. We can also look at this was binary thresholding, and the one that we saw over here, this was inverse binary thresholding. So we're done with binary thresholding, we're done with inverse binary thresholding. Now let's move on to some applications of thresholding. So this is a fairly interesting part because we'll get to know how to use thresholding in like real life scenarios. All right, so let's go ahead with the first example. So I have this image of animals in my system. This is a picture of animals on a green grassy field, and I want to generate a binary image which is white only where the animals are. So how do you think we should approach this problem?
The animals are all brown to black, so we can use their RGB values and filter by that RGB value.
Right. But could you be more specific? So the animals are brown to black, right? So which do you want to filter the entire image on? Do you just want to apply a threshold to the entire image?
We can check the parts of the image that have a low green and low blue and very small red, and that way you can filter it. So that's how you get brown. So
Yep, that is a viable strategy. So you can do that, but I think for doing that, you would have to write a loop that iterates over all the pixels, since you are using a custom condition to check, right?
yeah.
Instead of that, we can probably use thresholding and do it in a slightly easier way. we can, so in this case the entire image is dominated by the green color, right? So what we can try doing, uh, so I encourage you to try what you suggested on your own and see the results for yourself. Right now let's go on with the way that I am showing you right now. So let's first read that image. It's JPG. Since I'm not giving the second argument, it will automatically read that as a color image. PLTIM show cv2 dot convert color animals dot color bgr2 rgb. Alright, plt dot show. I did something wrong somewhere. cv2 has no attributes color bgr.
Underscore is missing of the color.
Yep. So we have this image now loaded into memory, stored in the animals variable. Now what I want to do is I want to look at the green channel of this image, because what I think is happening is that, so what you suggested is that we can look at the red and what was the other color that you were talking about?
Black.
Right. So if you are talking in terms of RGB color space, we can look at the red channel and we can find out the areas where red is lacking. Or we could do it the other way around. We could look at the green channel and find out the areas where green is lacking, because red is not very abundant in the rest of the image, so it could be lacking in the rest of the image as well. But green is very abundant in the rest of the image and very sparse in the areas where there are animals. So I think it would be a better bet if we try to threshold using the green channel. So if we split the image into Bgr, right, and I show you the green channel of this image. You see, it's pretty, like, you can clearly differentiate the horses from the background, right? Because of the like stark contrast in the green channel. So it should be pretty easy if we threshold it on the green channel. So let's do that. Let's write animal thresh equals cv2.threshold. Let's threshold this animals image. We don't want to threshold the animals image. We want to threshold the green channel of the animals image. I want to threshold it on some value. I don't know the value yet. The maximum value is 255, and we want to use the, so yeah. So let me ask you, what threshold, which threshold do you think we should use over here? Like, should we use thresh binary or should we use thresh binary inverse?
Thresh binary inverse.
Right, we should use thresh binary inverse because we are trying to color the places which have less amount of green with white color. Thresh binary inverse. Alright, and I'll just copy and paste the code to show animals thresh. Now if I run this code, I get an invalid syntax. Right, so we haven't yet decided what threshold we have to put. So let's just try 150. Let's see what happens. 150 is too large. The entire grass area is less than 100 less than 150. So let's reduce this. Let's reduce to 100. It's better than the previous one, but it's still very noisy. We can probably reduce it a little bit more. Let's make it 70. So we see that we have gotten rid of a lot of the grassy areas. We still see some noise in the image. So I think we can go a little bit more and reduce it to 50. And now we see that we have a very good mask of the animals that does not include a lot of noise. So yeah, this is one way we can use thresholding to segment out parts of an image based on um, some specific colors or specific intensities of the pixel. So is there any doubt until now? Okay, I see some chat messages. Are there any chat messages? Okay. All right. Really quickly. All right. So is there any doubt up till now?
So can we do something like compare neighboring pixels, and since these are similar, and we can just subject them, and whenever there is a difference like between the ground and the horse, there we get a value. So can we do it that way?
Right, you can do that way, but let's say you do it that way. But what happens when you are when you are evaluating a pixel inside the horse? Its neighbors will have a similar color, so it won't be colored white, right? So what you will basically
Yeah.
have is an edge of the horse.
Oh, yeah. I got it.
Yep. So this is actually an edge detection algorithm that you're talking about, and you will learn it in the second session that will start from 3 p.m. So you will learn it in that. Yep. All right. Great. So any more questions in this first example? All right, no questions. So let's move forward. Let's move to the second example. The second example. So in the second example we have. So in the second example we will try to segment out the red fruits and vegetables in the veggies image. So we have plt.imshow. I'll just show you the veggies photo once again. Let's run this. So here's the veggies photo once again, and we want to segment out this region, which is slightly reddish in color. We want to segment this out. How can we achieve this? Do you have any ideas?
The R value should be very high, the G and B value should be low.
Correct. So so one way we could do this is probably like take the let's just display the R value first, so everyone is on the same page right now. Everyone comes to the same page. So let's split the what's the time right now? Okay. So let's split the veggies photo into Bgr, and let's show each of these channels. So this is the code that we already had up there. I just pasted it again. So we have these three channels, right? So we want to threshold on the, so we want to somehow threshold on the R channel such that we don't have contributions from green and blue in uh, the pixels where R is high, if you get what I mean. So let's just try just thresholding on the R channel by itself. Let's see what happens if we only threshold on the R channel. So here we threshold on the red channel. We threshold on the red channel. We enter a value of 170 as the threshold. We perform the binary threshold and store the value in the red thresh image. And then we see the red thresh image. What do we see? We see that it doesn't do a very good job of separating the reds and the oranges. It seems like they go along together if we try to threshold using just the red channel. And it even seems like some of the white areas, some of the whitish areas are coming into the picture as well. So it's not a very good way of thresholding just by using the R channel. So I think we all agree that we need to add more information to this in order to threshold just the red fruits and vegetables. So one way of doing that could be taking the R channel and subtracting the blue and the green channel from the R channel and then thresholding on that. So that is something that I encourage you to try on your own. Right now we'll go ahead and use another method of thresholding based on hue saturation value. So I think, yep, there are no questions. All right, so we'll go ahead and use the thresholding based on hue saturation and value. So let's convert the veggies image into an Hsv veggies image again. So this is again the code that we had above. We create Hsv veggies by converting color from veggies from Bgr to Hsv, and we split this. We decompose this Hsv veggies into hue, saturation, and value channels, and then all we want to deal with right now is the hue channel, because if we scroll up a bit and look at this image, we can see that like we can pretty much separate the entire red region just by performing a clever threshold, performing a suitable threshold on the hue channel. So that's what we'll be focusing on right now. So let's just display the hue channel once. So again, you see there are a lot of artifacts right now in the red region. So if we try thresholding, so let's say we try thresholding all the values below 10. We try to select all the values below 10. Do you realize what the problem there will be?
So we miss values which are around 180.
Correct. So all the values which are, let's say for example, from 170 to 180, we miss all those values. So what do you think would be the solution to this? Like, how should we cleverly manipulate the Hsv image so as to like have a proper threshold on the R red hue? Change scale, how would that help? How would changing scale help? Could you elaborate, Aryan?
Sir, what if we replace the pixels?
Replace the pixels by what? Oh, you mean
So,
like color them?
yeah, so for suppose if we have a pixel value of some 75, we add some value of 30. So for each and every pixel in the total image, we add a value of 30. And for a pixel value which has greater than 180, I mean, if we add something such that it some exceeds 180, then we subtract that particular value with 180. So we are just rotating the colors on the cylinder which we have previously seen, such that the red comes out of that zero at the range of 0 180.
Yep. That's exactly what I had done here. So what he basically said was, also I would like to point out another solution by Shreya Vijay, is that we saturate hue completely and then split the image and apply our channel threshold. That could be a viable solution, but once you saturate the image completely and you split the image, you still run into the problem of, like, if you apply R channel threshold, you still run into the problem of getting the oranges included with the R channel. You get my point, right?
Yes, it makes sense.
Yep. Okay. So what Venkata basically said was, if we have this hue wheel, and let me just clear the screen. We have this hue wheel, and we rotate it such that the red region is not at 0 anymore. So let's say we rotate it by 5 degrees. We rotate this entire wheel by 5 degrees. So the new 0 would be somewhere over here. This would be the new 0. And where the old 0 was, that would be 5 degrees. And let's say we want, let's say we wanted to have a threshold of minus 5 degrees to plus 5 degrees. So after rotation, the threshold will become 0 to 10 degrees, right? Are you guys following me up till now?
Yes, sir.
Okay, great. If anyone is having any trouble, then like you can ask in the chat, or you can even unmute and ask me directly. All right. So after rotation, after a rotation of 5 degrees, we want to threshold at 10. I think this much is clear. So to rotate by 5 degrees, what we will do is we'll make a new image, and that image will be the hue value rotated by 5 degrees. So we added 5 to each and every pixel in the hue grayscale image, and then just like Venkata said, that so if any value exceeds 180, we will subtract 180 from it, and we will basically bring it back to this, or like starting on the circle. So an easy way of doing that would be to take the mod with 180. If you guys are familiar with that, np.mod of h plus 5 with 180. So if you take the mod, you guys know what mod is, right?
Yes.
All right. In case someone doesn't know, just let me know. I'll explain it. So when you take the mod, the values that are above 180, they get divided by 180, and only the remainder is left. So essentially you're subtracting 180 from it. So this is basically what we have. Basically we have rotated the H values by 5 degrees. Great. So now we can just perform a simple threshold operation. And what kind of threshold operation should we use over here? Should we just use binary, or should we use binary inverse?
So binary inverse.
Right, we should use binary inverse because we want the values from 0 to 10 to be white, to be elevated to 255. So we should use binary inverse. And threshold should be 10 because we rotated by 5 degrees and we wanted to cover the angles of -5 degree to +5 degree. After rotation it becomes 0 degree to 10 degree, so we want a threshold of 10. And over here we want H rotated. Before we do this, let's just have a look at the H matrix now. The H yep, let's look at H rotated first. So now we can see that all of those artifacts that we had, they're mostly gone. We have like pretty clear red color vegetables over here. So now we can confidently apply a threshold of 10 to all the vegetables, to the H rotated image, and we will display that over H rotated thresh, and we will display that over here. And you can see that although we have some amount of noise over here, we have like fairly accurately isolated the red region in the image. So that's how you can like use hue thresholding to your advantage. So just as a last small exercise, I want to use this mask to display the contents of the original colored image only where the mask is white, and rest all at the other places I want it to be black. So where this image is black, I want it to be black. Where this image is white, I want the color to show through. How would you achieve that?
So for the original image, we check the value of pixel, and I mean for this image, for the rotated threshold image, we check the value of the pixel at each point, and if it is 255, then at that particular location on the other image, we keep the image. I mean, we don't change the color, and in other places we change it to black.
Right, you can do that. You can make a loop that iterates through each pixel on both the images, and like it checks the corresponding pixels and it makes the changes accordingly. But there is a way easier method to do that using like the NumPy operations. So let's change this so let's change the maximum value from 255 to 1. What that will do is it will create a binary image where the black regions are 0 and the white regions are 1. The white regions are not 255, rather the white regions are 1. Apply Boolean equation on 2 Numpy arrays. Yes, you could do that, or you could like simply perform an element-wise multiplication. So both are similar, like similar concepts. Both are vector operations. So if you do this, something like AND operator. Yep. So what I'm going to do is basically multiply both the images together, and multiplying is similar to an AND operation. So yep, that's basically what we are going to do. Nice one. So I guess you can blur the image, then apply the mask. That would give a better output. Yep, you could do that. In fact, I think in the next session, you would be learning about techniques to blur the image, techniques to remove noise from the image, like salt and pepper noise, techniques to get rid of holes, techniques to fill holes. So those things will come in the following session. So once you are equipped with that knowledge, you can revisit this example and clean up this mask, and that would give a much better binary image for you to look at. So what I was saying was, let's create a new image called veggies masked, and that would be veggies multiplied by the H rotated thresh. So what this means is that I'm taking each pixel of the veggies image and multiplying it with the corresponding value in H rotated mesh. So if the H rotated thresh is 0, so the veggies pixel will be multiplied with 0 and it will become 0 black. But if the H thresh is 1, then the veggies pixel will be multiplied by 1 and it will remain what it is. So let's now display the it's very hard to find. Okay, let's now display the veggies underscore masked. Let's do that, and we get an error. What is the error? Operands could not be broadcast together with the shapes 408612 and 408612. So the error here is that we are multiplying veggies and H rotated thresh. H rotated thresh is a binary image, so it contains so its shape is 408 into 612. It's a 2D array, while veggies is a 3D array. It has 3 channels, so it's like we can't element wise multiply them together. So an easy fix for that would be just write np.atleast3d. What this does is it broadcasts this array into a 3D array. You can read about like NumPy broadcasting like in your free time, but what it basically does is if I'll just show you over here. All right. So if you had, let's say, a 2D array, and it had in this cell it had a value of 1. After applying np.atleast3d, this 1 will be replaced by bracket 1. So earlier it was just 1. And this was just, let's say, 0. and so on. But after applying at least 3D, it inserts an additional list inside each element. So now when you multiply them together, the 1 gets duplicated twice, 0 gets duplicated twice, and it becomes the same shape as the shape of veggies. It's a bit complex, but you can like read broadcasting in your free time. But what it basically does is it enables us to multiply these two matrices together, these two images together, element wise. And once we do that, we can get this. I'm not sure what happened over here.
You didn't execute that.
Yep. Yep. So once we multiplied them together, we have this final result, and it looks pretty close to like all the red vegetables are included in this mask. So it looks pretty good. Yep. I think with that we conclude this session, and the next session will begin at 3 p.m. If you guys have any doubts, we can discuss them right now.
Yeah, excuse me.
Sorry, could you repeat?
Yeah, in the above cell, I didn't get why how we replace that 255 with 1.
Oh, so if we say, if we write 255 over here and we multiply them together, then so wherever these are white, in those pixels, the veggies pixels will be multiplied with by 255. So they will become very huge value. We don't want that, right?
No. My doubt is that in spite of replacing the 255 with 1, in the output in that cell, we are even getting those red colored vegetables as white only, but the pixel value corresponding to the 1 will be near to black.
Right. So these are two different outputs. Let's look at this output first. So if I change the maximum value for this IM show to 255 and I run this again, you can barely, I don't think you can see any mask, right?
Yeah, now I got it. We need to replace the three maps in the second line.
Yep. So this is
got
true.
Thanks.
Yep.
One thing I wanted to, as we did here, we did the binary thresholding, so we are like having like the 1 and 0 kind of condition. But as I was trying to think about the range kind of thresholding, where suppose there is a human kind of image and we don't find any specific channel, like we are trying to find channels where we could apply this kind of binary thresholding possibility.
Right.
And otherwise, if we don't find this kind of channel, a specific channel, then what shall we do for, suppose if there is an image where there is a human standing maybe.
Right.
So his color space would not be that kind of binary, maybe in any color space that we are having.
So in that case, so it's not like this is one solution for all problems. This is a very this is a solution that you can use in a lot of places, but you can't use it in like every place. So for example, if you have a human, so a human can wear different colored clothes, can and like he can blend in with the background. Say for example, if he wears a pink shirt and the background is also pink colored, like you can barely distinguish him from the background using image processing techniques. So there is a limitation of image processing, but in most cases, like if you like, you can get away with doing some binary thresholding kind of thing. So for example, I participated in a competition wherein we had to build a robot that had a camera on top that would look down, and there were lanes on the road on a grassy field. There were lanes made of chalk powder, and you had to stay inside the lanes. So just by using image like binary thresholding, it was pretty easy to separate the lanes out of the grassy field because the grasses were all green and the lanes were all white. So you didn't have to use some kind of a like advanced um, machine learning or deep learning model for that. The disadvantage of using those kind of models is that they require very heavy computation, whereas image processing you can basically like very cheap. Image processing is very cheap like nowadays, especially with the like optimizations in Opencv and Numpy. So that's the benefit of using binary thresholding for segmentation. In fact, like you can see you can see the everyday use of binary thresholding in case of like movie production, wherein they use blue screens and green screens. So the reason for using those screens is that cameras are very susceptible to blue color and green color, and like the human skin has very less green color in it, so it is very easy to separate a green colored background from a human. So like those are those are the places where image processing is still the like leading algorithm, you could say. Like binary thresholding is still the leading algorithm.
Okay.
Yep. Yep. Are there any more questions? All right. If there are no more questions, I'll just take up a small topic really quickly that we should have covered. All right. Let's go to the threshold. Opencv documentation. So apart from thresh binary and thresh binary inverse, we have thresh trunc, thresh 2.0, thresh 2.0 inverse, all of these. So this illustration is very helpful if you want to get a quick overview of the different kinds of thresholding. We have the original image, which is a gradient. We apply binary thresholding. We get the brighter parts to be white and the darker parts to be completely black. Binary inverse is the exact inverse of the binary thresholding. The truncated thresholding, I think, so the truncated thresholding is that whatever value you apply the threshold to, that value will be the maximum value of the threshold, and whatever values are below that threshold will not be changed. So everything above 150 is brought down to 150, and everything below 150 remains the same, or like 128 in this case. I think half of 256, half of 256 128. Similarly, 2.0 is everything below 128 becomes 0, everything above 128 remains the same. 2.0 inverse is everything below 128 becomes remains the same, everything above 128 becomes 0. So that's that. Then we have adaptive thresholding. That's slightly complicated. Not as complicated, but it's slightly complicated. I think you will have a better understanding of adaptive thresholding once you are done with session 2 of this workshop. But it's very useful, adaptive thresholding. So you can see that like if this is the original image and you apply traditional thresholding, it doesn't give a very nice result. But if you use adaptive mean or adaptive Gaussian thresholding, it gives like a very clean result. So it's worth looking into. But I think you should probably do the session 2 of the workshop and then look into this on your own. Yep. So that's all I wanted to discuss about. I think there's a question. No, there's not. All right then. If there is no more question, like there are no more questions, then we can probably finish this session. It's adaptive thresholding. Does it change at base? Adaptive thresholding, does it change at base based on general background color? Yes. So basically, how adaptive thresholding works is that if you have so whatever pixel you're applying the threshold on, it checks the nearby regions of that pixel, and whatever the average intensity of those nearby regions is, it changes the threshold according to the nearby intensity. So if there is more intensity, it will increase the threshold. If the nearby regions have less intensity, then it will decrease the threshold, something like that.
So, I mean, can I ask a question like, not exactly related to the session?
Okay. What is the question?
So, in your wallpaper, I can see a Mandelbrot image. So, like, is there any way to create those types of visualization using this sort of techniques? Or
All right, I'll answer this question. Give me 1 second. Thank you, everyone. I really hope you liked the session, and thanks for the wonderful comments. And yeah, all right. So the session is over now. I'll stop the recording 1 second.